Looking at the motion of galloping, notice how different this motion is from the aeolian vibration we saw before. We will now pan down the line and look at the galloper, which is driving the span. This particular motion has very long loop lengths. End and look at the suspension point. We have very long loop lengths. This actual span is approximately 25 meters in loop length. The amplitude of galloping motion is approximately 1 meter. You'll also hear in the background a clunking which is occurring. That is because due to the galloping activity, the forces of gravity are being overcome and the suspension clamp is lifting up and hammering down on the hardware fitting. And this is causing a very high loading on the suspension. This happens to be the fiberline suspension which is used for optical ground wire. The fiberline suspension is a modification of the armor grip suspension and utilizes a rubber elastomer cushion element which goes around the optical cable and then is held in place with the suspension rod you see here. Now, as the cable is going up and down and galloping, we are having high bending stress due to the galloping motion, and also you will notice a longitudinal stress, and this is typical of galloping. In aeolian vibration, you only have stress due to bending. This we have stress due to bending, and we have stress due to a longitudinal axial loading. For this particular device, we have a strain gauge mounted to it to record the peak bending strain, or in other words, how much damage is being done. In the previous test, we used a displacement transducer to measure the amplitude of motion. In this particular device, we've taken an electronic instrument called a strain gauge and glued it to the steel wires. The strain gauge has output, you can see here, in what we call a strain trace. And this is the galloping activity that you are seeing occur. This line right here, from this line to this line, is a 1 second time interval. And as you can see, it goes through one cycle, 2 complete cycles in that 1 second time frame. So in other words, it's galloping at a 2 hertz. This is the first resonant mode of this cable for this span. This magnitude here is indicating the amount of damage that's being done. For this particular test configuration, we're seeing 815 microstrain of damage. Microstrain is a measurement of how much damage is being done to the cable, and right now we are exceeding the endurance limit, and if we keep galloping for long periods of time, failure would occur. Now in the laboratory, we can gallop a span such as this for approximately 10 to 15 hours without failing the cable. But if we would go longer, it would fail. In the real world, galloping is much more destructive, and that's because the spans are much longer, and therefore the conductor has a lot more mass to it. So there are limitations to how much damage we can simulate in the laboratory in comparison to the real world damage that's being done in the field. In the real world, where you have a 300-meter span, you can imagine the amount of mass of the cable as it oscillates up and down causes much more damage to the hardware at the location. Occurrences have been noted in the field that we can find failure of cables due to galloping in a few hours of time frame. It has been known at times for galloping to actually occur over a few day period, but generally speaking, galloping is a short-term damage activity that can occur on the line. We will pan down the line once again so that we can take a look at the overall galloping. Very long loop lengths, very large amplitudes, very destructive motion. Notice how different this is from the aeolian vibration we have just discussed earlier.